Okay, good afternoon. This morning we ended up just here. So now we have to look at some algorithms that we are going to use in the frame relay framework, and mainly looking at policing or conformance verification on one end through the leaky and token bucket algorithms, and congestion control in the two fashion which are named backward and forward. So let's start with conformance verification. So what's the basic idea? Now we know that we negotiate three parameters basically, CBS and CIR. CIR is an average rate. CBS gives us indirectly the value of the time window over which we are going to verify and guarantee the average rate, and excess burst size to send something in addition to that. So the intuitive idea of the conformance verification is the following one. So suppose that a packet reaches the network access and it is conformant to what is contained in CBS over T. Remember that we can spend up to CBS bit or byte over capital T. It is transmitted at high priority, so with the discard eligibility bit set to 0. If instead the packet reaches the access and it is not conformant to the CBS, the committed burst size, but it is conformant to the CBS plus EBS over T, it is transmitted as a low priority packet with the bit set to 1. If a packet instead reaches this access point and it exceeds the summation of CBS plus EBS, it is discarded. I'm not sure I said something correct about the second point, but what is written here is instead correct. So it exceeds CBS, but is below CBS plus EBS, it's low priority. If it exceeds CBS plus EBS, it's discarded at the network access. The same algorithm can be used to do the shaping, whereas you change the marking and or dropping feature. The first step we have a marking, and then in the second step we have a dropping with a delay. We add a delay so that the packet becomes conformant to the negotiated profile. So shaping is the traffic adaptation to make the traffic conformant if it was not originally generated as conformant. So this can be done through traffic regulators. There are two main types of traffic regulators, plus some, of course, a more complex version that we will see later. The easiest one is called leaky bucket. The leaky bucket is a traffic regulator in which you have here, so you have traffic entering the network, so generated by the user here on the left-hand side. This traffic is stored in a temporary buffer up to a given size, just because we have to limit the buffer for practical reason. And then we have a regulator at speed rho, which basically allows this packet to get into the network. So we are describing the leaky bucket as a shaper here. Okay? So here you have a gate, and the gate opens at a speed which is the inverse of rho. Okay, so the larger the rate, the more frequent, sorry, it's not the inverse, it's directly proportional to rho, so the larger the rate, the higher the frequency of admission of packets. And what's happening is that at the output of this device, the traffic generated by this user is not worse in terms of being more aggressive than a CBR source at rate rho. So you may generate the traffic as you wish. Of course, the long-term rate should be equal at most to rho, otherwise you will saturate this buffer and start discarding packet. But even if you do that, it's not a problem. But at the output of this regulator, any traffic generated by the user is translated, is transformed in a CBR source at rate rho. Okay? Now you have some details, because if you account rho and you implement rho as simply a timing behavior, this is working properly only if the packet size is fixed. Otherwise, you should account for the packet size to determine the next starting time. You know that the CBR source is such that the ratio between the packet size and the inter-arrival time is constant. So if for fixed packet size, the inter-arrival time is constant, if the packet size is variable, you have to adapt also the inter-arrival time, but this is a trivial extension, okay? If you want to use the same device for conformance verification, so you assume that the source should be CBR source at rate rho, simply any packet that is received and that should be stored because it's received earlier than the permission, what's happening is that it's going to be dropped. So this is how to use a leaky bucket for a not for a regulator, but for a policer, okay, for a conformance verification. So in other words, you may have an input traffic which is absolutely random or uncontrolled, and at the end of output of the leaky bucket, what's going to happen is that you will have a CBR source such that in this case the picture has constant pi, but such that pi over ti is equal to rho for any I, okay? For any time interval. So that's what you see at the output. So you translate anything, any type of user traffic in a CBR source at that rate. Clear? Okay, so you can account for, if you have this regulator, you can account for this type of source as if it was a CBR source at that rate. Yeah. Do what? The buffer size is not really a critical parameter because we are dealing with rate only here. So if you generate too much, it's going to happen that you will drop some packets, but normally this is not happening. So we can, of course, if you assume infinite buffer size, you will never have packet drops. The amount of data that you send over a period of t is t times rho. And the problem is that this is good if you have a source which is with a very low level of burstiness, okay? But as soon as you start to have some burstiness, you have a difference between the peak and the average rate of this source, so it's a variable bitrate source. If you assume for rho the average rate, you will start discarding packets or delaying it very, very much. And on the other hand, if you assume for rho the peak rate, you will waste a huge amount of bandwidth because you are accounting for this VBR source, which on average is running at BM, for a peak rate, which is the rate that you allocate, which is equal to VP. And you know that the ratio between peak and average can be up to 10 or 100. So basically, this type of traffic regulator is not really admitting any burstiness, is not really suited if you want to deal with the VBR source. So we need to extend this model. So the more popular traffic regulator, which is called token bucket, which can actually degenerate, if you wish, to the leaky one, with token size equal to 1, is the one depicted here in this slide. So we have again the source here on the left-hand side, you see. We have a regulator that gives permission, so it's like having a gate here, and when you open the gate, one packet get out. And then you have the network on the right-hand side. And you have a token here, which is not for storing packets. So you have a bucket in which you put tokens there, up to a given maximum size equal to beta. And you generate rho token at a rate which is rho. So rho is the token rate generation. So you put tokens in this bucket at the speed rho, which is a constant rate. You can accumulate up to beta of them, and then as long as you are not using one token, you cannot add another token to the bucket. So the maximum number of tokens available at any time will be bounded by beta. And the rule for regulation is that you generate as you want, and you can get out, you can get sent in the network only if there is one token. So you generate a packet, the packet waits until there is at least one token generated. When there is one token, you get the token, you get out, and you throw away the token. Okay? This works well if we assume, again, a one packet per token under the hypothesis that the packet is of fixed size. Otherwise, you should adapt these, instead of accounting for integer number of packets, you have to account for a given number of bytes. So a token is the permission of sending a given number of bytes. If the packet size is smaller than this amount of bytes, you can send it. Otherwise, you have to wait until you have enough bytes. It's just a straightforward extension, okay? Clear? So tokens are generated at a fixed rate rho. A maximum number of beta tokens can be stored. And that allows for some burstiness. Why is that? Well, imagine that you want to create the most bursty traffic that you can create on this network, knowing that you have this token bucket that regulates the traffic. Okay? So you want to generate as much burstiness as possible. Okay? You want to be compliant according to this regulator, but being as aggressive as possible by being compliant. So what you can do, which is the maximum burstiness that you can try to put in your network. Yeah, you can suppose that you want to generate burstiness. To generate burstiness, you need to have tokens, right? Because if you don't have token, you can generate as many packets as you wish, but you don't get anything out of it. So the maximum number of tokens that you can put in your bucket is beta. So you have to wait until you create an amount of tokens equal to beta. At that point, you can reach the access point at very large speed. And what you will generate on the network is a set of beta packets back to back, if you don't have further regulation. And that's it. Because after beta, even if you have generated millions of packets, you have to stop waiting for the next token. So what I'm saying is that if you want to be very, very aggressive, the most you can do is that you can generate up to beta packets back to back. I'm always simplifying, assuming fixed packet size, but the extension to variable packet size is absolutely trivial. That's the maximum burstiness. Burstiness means that you generate a huge amount of data. And then after that, what you can do? You have to wait until what? Excuse me? Yeah, so one approach we say, okay, I had put my packet in the buffer waiting until you have generated beta tokens. Then I put a huge burst of packets there. So what's going to happen? I send beta packets back to back. And then I have a lot of packets waiting for what? Waiting for a token. And the token from now on is going to be generated at a rate which is rho, correct? So what's going to happen if you have a huge amount of packets already available there is that you will generate from now on in such a way that this rate is related to rho, the token generation rate. Okay? So that's one possible behavior. So after this burst, at the beginning, you are again behaving as a CBR source, which is, of course, a source whose burstiness is 1. Okay? Another thing that you can do is that you generate exactly beta packets when you have beta tokens. Then you wait again until you have beta tokens, and then you can generate again beta packets, right? That's another possibility. So what you can do is that you can say, okay, I will generate here beta packets here, as before. Then I'm going to become silent for such a time that, well, large enough to create again beta tokens. Okay? And then at that point, if you generate again beta packets, you can send them back to back. So you will have another burst here. Clear? That's more bursty behavior than the previous one, correct? Do you agree? That's the maximum burstiness you can create. You can repeat blocks of beta packets one after the other one, and then you have to be silent and then repeat and repeat and repeat. That's another possible behavior. And any intermediate behavior or something that is generating less than that, it's of course fine. Everybody agrees on that? Yes. And this is exactly what's happening. If you compare these two generation processes, the second one appears to be much more bursty, and indeed it is more bursty, even if formally they have the same burstiness parameters. If you define the burstiness parameters, the burstiness parameter is exactly the same for the two types of traffic. Clearly, the second type of traffic is creating more complexity in your network because you have to continuously deal with this block of beta packets back to back, which will fill up your buffer, etc., and create more problems to other flows. But the second generation process is never faster than the previous one. In order to create this burstiness here, you have to be silent, and you see that the rate here with respect to the other flow is smaller. In order to create burstiness, you have to go back to the average rate, globally speaking, so including the burstiness. You create a burst, then you have to become silent in such a way that the total amount of bits is comparable with the amount of bits that you would have sending on a regular basis on a CBR flow. At that point, you can create again the burstiness. So every time that you create the burstiness, before doing that, you have to reduce the rate of the source to accumulate tokens. And this holds also here for the first burst. It's not represented in this picture, but also for the first burst. In order to create it, you have to become silent for a period of time in which a CBR source would have generated exactly those beta packets, because you have to accumulate tokens. And then you can create the burstiness. So first you pay, and then you gain burstiness. That's how it works. And once you've gained the burstiness, to gain it again, you have to go back again to exactly to the average rate. Otherwise, you are not able to gain any burstiness at all. Okay, is it clear how it works? So you have burstiness. The burstiness is regulated by the amount of tokens that you can accumulate, which is beta. The larger the beta, the more bursty behavior you can have. But burstiness should be gained by being silent or by sending slower than the raw rate, which is this rate here of the token generation process. Is it clear? Yes or no? Hello? Good. Okay, normally in practice what's happening is that you have a user generating some traffic and you will store this traffic in a buffer, both for the leaky and the token bucket. For the token bucket here, the user buffer is not represented. So you have a buffer here. That's normally what's happening. And all these type of regulators are gates that open up when you have the permission to send. So you can implement them through counters, you can have different variant implementation, but conceptually is a permission to be sent out of the buffer. Okay?
The more you want to parse the traffic, the more you slow down your rate.
No, yes and no. The more you want to be bursty, the larger should be beta.
Yeah, okay.
But in order to accumulate up to beta, you have to wait longer. Yes, absolutely.
So it's possible that you can go even below your average rate.
Yes, all of the things that we have said up to now are worst case. Typically, any source is going to behave like this or better. Better means sending less. That's the worst case, not more than that. So you can make your computation assuming that the source is going to behave in this way, which is the worst possible scenario. Okay. In practice, it's always going to be better than that. Yeah, absolutely. In what sense? What a token is? It's a permission to send. So you can implement in so you can see it as a token that you put in a basket, and then if you want to get out, you have to look in this basket and say, okay, there is a token, you take it and you send it out. Or you can have a counter if you prefer. Okay, so you increment this counter on a regular basis up to a maximum value beta, and when you want to send the packet, you look at this counter. If this counter is 0, you cannot get out. When this counter becomes at least 1, you send it out for fixed packet size. For variable packet size, everything the same. The only difference is that you have to take into account not integer numbers, but number of bytes or something like that. It's more clear now? It's a logic representation that you can implement in different ways, doesn't matter, as long as it's working in this way. So, tokens are generated at a fixed rate. User data are sent over the network only if there is a token available in the token buffer. This is a summary of the rules. The maximum amount of data that you can send over a period of t is t times rho, which is the number of tokens that you generate over t, correct? T times rho is the number of tokens that you generate, so at most you can send this plus the burstiness, assuming that previously you have accumulated some burstiness, not more than that. In any time window t, you will never generate more than that, okay? The source becomes a VBR source in which the average rate is what? The token generation rate. Because if you can send a packet only if there is a token, you have a rate of process of generation, your average rate is going to be bounded by that value, correct? The token generation rate is the average rate. We have to deal with this time window measurement, of course. We have to compare them, but roughly speaking, the token generation rate is the average rate of this source. The peak rate, if you don't further bound this controller, is the access rate, because you can send packets back to back. If you want to further control the peak rate, you can cascade to the token bucket a leaky bucket with a different rate rho. That will further control the peak rate. You can reduce the peak rate with respect to the access link speed, if you wish, by adding a leaky bucket. Of course, in this case, rho 1 is going to be larger than rho 2, otherwise it doesn't make sense. Okay? And the burst duration is basically, roughly speaking, the number of packets equal to beta. So this intuitive description that we made, okay, we have to characterize our traffic, if you remember, through peak rate, average rate, and burst duration. Burst duration is beta, the peak rate is the access rate unless you have a leaky bucket cascaded to this one, and the average rate is the token generation rate, okay? In this case, we will have a source which has a burstiness in terms of burst duration, if you measure the burst duration with the number of packets equal to beta, an average rate of rho 2 and the peak rate of rho 1. And these are the typical, the three parameters that we require for characterizing VBR sources, okay? Questions? No. Okay, so these are a couple of pictures now in which we try to describe what's happening in this process. It's not exactly so trivial as I have described it up to now. Why is that? Well, let's go through this example. So what we have here, okay, on the x-axis we represent the time, and with an arrow here we represent the arrival of a given packet at the user to network interface, okay? So in this example we will have, in this time window which has length equal to t, capital T, okay, 3 packet arrivals, here, here, and here, okay? Clear? What else we have? We have here the amount of bits sent for this virtual circuit, for this DLCI. The amount of bits sent increases with the access rate because we send each packet at the access link speed, correct? So when we serve packets here, this is the packet arrival, we start serving it now, this line is parallel to the access rate link, because we are sending that packet at the access rate, correct? When we send the packet, we send at the transmitter rate. This line here represents the CAR. Why? Because over T, we are generating CBS bytes. So if this is CBS and this is capital T, this line here is the average rate named CIR, because in the CIR, we are generating exactly CBS bit over capital T, if you remember the definition of T, CBS, and CIR. Okay? Is it clear? So this is CBS. Suppose that we have this value of EBS, the XX. CBS plus EBS is something that we can send only with the DE bit equal to 1. Okay? clearly CBS plus EBS should be an amount of bits smaller than this value here. Why? Because otherwise we are giving to the user the possibility of sending more than the access speed link, which doesn't make any sense. Okay? So regardless of the absolute value for CBS and EBS, you can choose them freely, but the summation of the two should be smaller than the amount of bits that you can send if you were continuously using your link for bit transmission, which is this value here, over T. Is it clear, this picture here? So this is the access rate, this is the CIR, this is CBS and CBS plus EBS. This difference here is excess burst size. Now what we want to do, everything that is generated with this bound of CBS over T should be sent at high priority with the bit set to 0. Everything that is being sent exceeding this CBS but being below CBS plus EBS should be sent as low priority with this bit set to 1. Everything exceeding the summation of the two should be discarded. That's the logic of our control. Okay? So in this example, we have one packet arriving here. We generate, you see that we generate and we transmit this at the access rate. Then we have to wait because the packet is finished for the next one. And then we send this one. And then we send this, wait, we send this one. And you see that all of those packets are below the CIR. All of those packets are conformant. We can send them at high priority. We are below these limits here of CIR. You see? We are always below CIR. So all of these packets are sent as high priority one. They are conformant. Okay? In this example, we have more packets arriving, in particular 1, 2, 3, and 4. So the first packet arrives at time 0. We start it immediately. So you see that at this point, we are a little bit above CIR. But this is fine, because we are going to measure CIR over T. So we know that we can have shorter period of time in which we are sending a little bit more than CIR. It's not an issue. Then the next packet is sent, and the next packet is sent. And now look at this one here. If you look at what's happening in T, if you send also this 4 packet, you see that we are exceeding CIR over T. We are sending more than CBS. This value is larger than CBS. Correct? So it means that this packet is not compliant. The size of this packet is too large, or the time at which we have received it was too early. So we can send it, but at low priority, because it's exceeding CBS over T, but is below CBS plus EBS over T. So it's admissible as low priority. Okay, so we have to mark the last one as low priority with this bit set to 1 to be compliant, to be proper with the negotiation. In this fourth example, we are receiving again 4 packets of larger size, and in this particular example, the first 2 are at high priority. The third one is already at low priority. You see that it exceeds CBS. The third packet is sent as low priority. And the last one should be discarded because we are exceeding the summation of the committed plus the excess. So we have to discard it. Okay? Clear? So everything seems fairly easy, I think, and it actually is not so complicated, with some caveat. And the caveat is the following one. We actually have a measurement problem that I disregard completely. And the problem is that of measuring a rate of an asynchronous packet arrival, which may be slightly complex. What do I mean? Well, to be properly correct, we should ensure that we are not sending more than CBS over T on any time window of duration W. So the previous example were a kind of trick because we have seen a static scenario, right? We are considering the connection is starting at time 0 and we are only analyzing what's happening in the first period of T. But indeed, this property of not more than CBS over T should hold for any time interval T. So to be really precise, we should have a moving window, and on any window of duration T, we should verify whether we are compliant with the CIR or CIR plus CBS plus EBS or whatever, to be correct. Is it clear? Which is something that in this picture we disregarded completely. So we have actually a continuous process, and we should measure this average rate in a continuous way. So how can we do that? Well, there are some simple ways of doing that which are not perfectly correct. The first thing is to say, I don't care. I'm measuring time window of duration t, and then I'm moving to the next t. So I'm analyzing separate windows, completely independent, fixed length, time interval examination. That's fine. I mean, this is an approximation. It may be okay, especially if the time t is not very large. It may be more than okay. If t is very large, it's not so good. And of course, clearly you see this example that at these two, suppose that these two interval 1 and 2 are the traffic generation process in these two intervals is compliant. But if you will analyze maybe in this area here, you may detect that it is not compliant, right? But you don't do that because they are not overlapping. So there is a mistake in doing this approximation. You may have actually a time window which is not represented here, over which your traffic is not really compliant, okay? You may say, I don't care, it's fine, that's an approximation. As I said, if this time window is not very large, it may be reasonable. Of course, the real issue, the formal issue are when we have to start the interval, if there is a border effect, what do? You take this into account or not, and all this kind of thing. Another solution is to have a temporal sliding window. Now, the problem is that if you consider a timeless window, that should be continuous, okay? But you can approximate it somehow. Let me give you an example about that. So suppose that this is the real generation process, okay, that you have. Something like that. Now you should come, of course, that's meaningless to start earlier than this time here. So you will start with a time window of t here, of this duration, and then you should continuously move this window, okay, and continuously check on any time interval what's going to happen, okay? Now, the first approximation may be that instead of doing that it continues, you may say, okay, I will verify for this t here, then I will take a t starting from here, okay? And then you can jump up to here, because in this interval there is nothing which is happening, so it's useless to check by moving in this time window. So you can do some type of approximation of this, right? That's possible. In order to make it work, you should keep into account, in general, if you have a moving window, you should account for any packet arrival time in the past, in the recent past. You should remember it, and the packet size, if you want to do a proper computation, okay? So you move, you have a window, you have to make sure that within this window, how many bits were generated and when, and you can do the computation. Then you move a little bit, and you do that again and again and again. So this process is fairly complex, okay? Even if you try to discretize it a little bit, and especially it requires that for each connection, this process must run at packet time, so high speed for each connection independently. So if this node has many, many users accessing, you have to do that independently for all of the users. So it's not a difficult algorithm, but it must run very fast, and it must run for any user that accessing the network through this access point, which may be not a negligible number. So simplifying it may be wise. So another way is to say, no, I don't do that. I will keep moving here when there is an event. So I will only examine the window when there is something which is going to change in my system. So when I have a new packet arrival, basically. And instead of accounting for every packet arrival time and every packet size, I will simply compute how many. So let's consider T1, then T2, T3, T4, and T5, etc., etc. These are the time and you synchronize them with packet arrivals. So when you analyze T2, you want to avoid to go back in the past to analyze what happened, okay, to make a proper computation. But you have a notion. You have the ρ1 rate, which is the average generation rate, the amount of bits sent in period 1. Okay, so let me call it not ρ1. ρ1 is not a good idea because ρ is a rate. Let me call it P1. P1 is the amount of bits sent over T1 that you know, okay? P1 over T1 is a bit rate. So what you are going to do in T2, instead of remembering that you got a packet here of this size, etc., you will say, no, I assume that up to here, up to the previous interval, I had a continuous generation process at this rate. Okay? So you spread out the amount of bits that you have in the previous pass uniformly in your time period. So you have to account only for one number, basically, not all of the past history. Okay? And then you adapt the new packet that you have, and so on and so forth. So basically, this is a fluid approximation of our system. Okay? I'm measuring a given time window, I get an average rate. Okay? I account for this average rate in the next time window for the time in which I don't have information, okay, in the past, and then I add the new bit, and so on and so forth. So that avoids the need of remembering any packet arrival time and any packet size, basically. You just remember one value, which is the rate in the previous window. That's an approximation, better than the one in which you have completely non-overlapping time window. Okay? I don't want to go into the details. There are many, many other things that could be said. It's just important, and this is true for many, many of the algorithms we are going to see. We are going to skip the specific details of most of the algorithms. Okay? What is very important for me, besides the specific algorithm, is that you are able to think about pros and cons of each algorithm, of each solution, advantages, disadvantages, simplification, implementation issues, etc., etc. Because within this, which is a very simple and trivial algorithm, there are many, many options, many, many possible variations. It's not worth to go and to discuss them in detail. But it is important that you get the feeling of which are the parameters that have an effect on that. And always is a trade-off between complexity, implementation issues, approximation, etc., etc. And you have to balance that depending on your goal. So if you want to be perfect, you should remember any packet arrival and any packet size for a given amount of time, and you do a more complex computation. The question is it so important? Probably not. So any approximation that makes sense is acceptable. But we know that it is an approximation. Okay? There was some, yes, raising hand? Yes. Exactly, as a fluid arrival. And then you consider the real, yes, exactly, to avoid keeping a too long history. Now, all of those issues are minor if the window is small, of course. So when the window becomes a little bit large with respect to with the packet transmission time, then it may become not so negligible. Take into account that these pictures are not scaling, because here we are talking about packet transmission time of hundreds of nanoseconds, maybe some microseconds, not more than that. Typically, these time windows are much more, order of magnitude more than that. So within one window, we'll have many, many packets. Okay, in that case, it becomes complex. If in one window you have two packets, you may say, who cares? I mean, it's not a problem. Okay? Any further question? Okay. So this is what is written here. It's the fluid approximation part. Okay, it is possible to exploit a fluid approximation. The new rate estimate as each packet arrival. At packet arrival, we assume that the flow was transmitted in the past. Rho times t, where r is rate and t is the duration of the window. And then you update, of course, the estimate and so on and so forth. So even this problem, which looks very, very simple, almost trivial, is not really so trivial at the end. Okay? Any further question about it? As I said, we are seeing this algorithmical part for frame relay, and in particular, we have adapted them to the frame relay framework, but this concept can be generalized to any modeling of CBR or VBR source in terms of either conformance verification or adaptation. Okay? Now let's move to another topic which is largely more important, which is congestion issues. And again, we are discussing congestion issues for the first time here in the frame relay framework, but most of the things we are going to say hold for any congestion control scheme, regardless of the specific technology supporting it. There are many general concepts that I will keep repeating, so please stop on them and think about them, because they look easy, I mean, it's just discussion, but behind any of them there is an important concept that you have to assume and you have to memorize and really understand. If you don't do that, you will not be able to repeat, because there are too many information about that, and especially even if you repeat and I will ask you to motivate that, you will not be able to do that. And we are an engineering class, okay? So repeating things because it's written in the slide is not good from the examination point of view. Actually, it's very bad. My interest is that you understand things, not that you repeat because it's written. So sometimes you come to the exam, you say, and you repeat exactly the sentence, and they say, okay, but what does it mean? And if you say, I don't know, or you don't demonstrate that you really understood the meaning of the sentence, even if you repeat it, is, no contribution for your examination. So try to follow this part, try to read, try to really understand, not memorize. So what congestion is, informally, is too much traffic on a given output link. Too fast for the network to be able to handle it. More formally, we already defined it this morning, is an average input rate larger than the average output rate. What average means we have to define. Congestion signals are long delays or increasing the delay due to queues in router or switch buffers. Lost packets, buffer overflows at routers, nodes, switches. Effects of congestion, well, retransmissions, not always. For reliable traffic, almost always. For traffic that has some tolerance to losses, it may just translate in a packet loss. It depends, but very often it implies retransmission. And as a consequence, it implies throughput reduction. And let me give you an example that makes it not so trivial, the effect of congestion, because you may say, okay, I have a link which is congested, I'm dropping some packet. At the end, if I have 10 megabit and I have 10 sources, all of them will get more or less 1 megabit per second, so it's not a big deal. Even if I'm generating a little bit more than 10, at the end I will get 1 times 10 sources is 10 megabit, which is what I can get out of the network. So you may have this intuition that congestion, yeah, it's bad, I'm dropping packets, but at the end, what has to go through is going through anyway, right? Because the link is there and you are keep sending and transmitting bits. It's not exactly like that. It's a little bit more complex. So let's examine this example for a moment. The first objection to what I said up to now is that I was completely disregarding retransmissions. So retransmissions are an issue because retransmission actually increase the load. So that lambda ij we were mentioning this morning is the average rate which includes retransmission. So if you have a given generation rate of the source, everything that you retransmit may add up to the traffic that you already generate. So only for that reason, you may even have a further exacerbation of the congestion problem for retransmissions. Now that depends on which mechanism you use for retransmission. It's not always true, but that's the first not completely correct picture that according to what I said before. We have to remember that any packet drops may imply an increase in the load for retransmissions, okay? And then it's even worse than that. So let's consider this example here. In this example, we have users, 4 users, A, B, C, and D. And we have 4 nodes, 4 routers, 4 switches, for whatever. Of course, we have buffers, and we have a traffic which is going in a clockwise direction here. So the source is generating toward a destination which is reached in a clockwise fashion on this ring. We have a ring here with a 2-hop distance. So A is generating towards C, B is generating toward D, C is generating toward A, and D is generating toward B. All of those are routed in this ring in a clockwise direction, so they interact on the same link. Okay? In particular, on any link, we have two flows interacting, you see, the red and the blue here, the green and the red here, the green and the violet here, the violet and the blue here. And of those two flows which interact, one is coming from a user link, and the other is coming from another node. So let's consider this link here in which there is a red and the blue flow. The red is coming from the user to this node. The blue is coming from a user through another node. Is it clear? And this is true for any link, for any conflicting pairs of connections. If you come here, you have a green and the red one. The green is reaching this link directly from the user. The red one is reaching this link passing through another intermediate node. Is it clear? So suppose what happens if you have a red traffic which is increasing. Now you see that you have a contention on this buffer between the red traffic and the blue one. But the blue one is bounded somehow in terms of speed by the fact that it's sharing already a link with the violet one. Do you agree? So if on this link you have a speed of 100 megabits per second, okay, the blue, and if there is fairness here in accessing this buffer and in scheduling and everything, these two flows will get 50%, correct? So 50 megabits for the blue one and 50 megabits for the violet. Not more than that for the blue, for sure, right? Do you agree? And on the other end, the blue is sharing this buffer and this link capacity with the red flow, which may come and reach this node with an unbounded rate, because there is no conflict. So the red flow can reach this buffer if all of the link speeds are the same, twice as fast as the blue one, in this trivial example. But if the access link speed is larger, it can be 10 times more, 100 times more, I don't know. In a more complex scenario, it can be under order of magnitude more than the flow we are considering. It depends, okay? In this example, if all of the links, including the links to which the user are connected to the nectar, are of the same speed, the red flow can reach this node with an access speed which is at least twice as the speed of the blue one, okay? And we have a congestion point here. So what's going to happen is that we are going to fill up this buffer. So in the filling up process, what's happening? It's happening that the red flow will insert a larger amount of packets with respect to the blue one, correct? Statistically speaking, you come fast at a speed which is twice, you will see 2 packets of the red flow in that buffer, while you see 1 packet of the blue one, because you are speeding up twice than that. And then what happens? And then you have the buffer which is filled up. And you can get in only when there is 1 transmission. But when there is 1 transmission, there is 1 chance, statistically, for the red flow, which is coming and reaching this buffer alone, and 1 chance in which you will get 1 red and 1 blue packet, and they will come in with equal probability. So not only you will have more red packets while you are filling up the buffer with respect to the blue one, in a ratio which is 2 to 1, roughly speaking. Okay, you have twice as much red packet as the blue one. But when the buffer is filled up, the chance for the red flow to get in is larger than the one of the blue one, because you have 1 slot on average in which you have only 1 red packet reaching the node, and 1 slot in which you will have 1 red and 1 blue one. And this can be much worse than that if the rate at which the red flow can reach this node can increase and increase and increase, unbounded in a very large way, okay? So if the red flow speed increases and there is no control about that, the blue flows is going to be shut off completely. Suppose that the red flow is generating always very, very high speed. Whenever there is something which is available in that buffer, you will put a red packet there, and the blue will never have a chance to come in. Okay? And so the throughput of the blue flows goes to 0, but the traffic that you generate on this link is not 0. So whenever you have a packet drop, you are not only losing that packet that you typically will try to retransmit, but you are also losing all of the upstream capacity that you have used for this flow. So if whenever you drop a blue packet here, all of the capacity that you have exploited to have this packet reaching this link is also wasted. And that's the real problem of congestion. There may be and this is of course a very trivial example, very simple one, but you may have much worse scenario than that. So that's the real negative effect of congestion. When you have a packet drop, not only the throughput is reduced, you have to retransmit, you have an increase in traffic, all of these things are correct, but furthermore, whenever you drop a packet, any upstream transmission capacity used for that packet has been wasted. So it's lost. Nobody else has used it. Maybe the violet flow could have used it, but you don't know. You didn't know that at that time, so how can you do that? That's the real problem of congestion. That's why congestion is so bad in a network. Is it clear? Okay, so we have described the problem. And so I hope that you are convinced that it's a bad problem. So what we can do to solve it? Well, you may say, well, what's the big deal? Increase the buffer size. The buffers are there to save and to avoid dropping packets. The larger the buffer size, the more packet you save, the less packet you drop, right? That makes sense. True, but only up to a point, because this is not going to solve any permanent overload. So any buffer-based solution is a transient by definition. So the larger the buffer size, the longer is going to be the transient in which you save packets. But sooner or later, since the buffers are finite by definition, you will end up in a scenario in which you have an average rate drop, which is the difference between the input rate and the output rate. So that's just a temporary solution, very short time. It's not changing the nature of congestion. It's not really solving the problem at all. You can put as much buffer as you want, okay? So for permanent overload, the excess traffic is lost, full stop, regardless of the buffer size, unless you analyze the system on a very short time scale. But this is not so interesting. You may say, well, one solution may be to increase the link speed. Now, this is not really practical, as we have said, because it requires changing the interface card. So it's a solution that you can adopt if you have a permanent congestion every day from 2 p.m. to 4 p.m. It's like, you know, there is a highway which has only 2 lanes, and you know that every day is going to be congested. Now, the solution of adding 1 lane, it makes sense in that scenario. But this is not what we are talking about, congestion control. That's not congestion control. That's network planning and design, something different, okay? And furthermore, you may solve the problem there, but then you may turn out to induce another problem in another link. Because maybe you solve that bottleneck, but then may create another bottleneck downstream. You don't know. So again, not necessarily this solves the problem. You may increase the processing speed. That's the worst thing that you can think of, because the congestion is not related to processing speed. Okay, it's not like that. It's another type of issue. And in any case, even if this was the problem, that for the same reason as above, for the increasing of the link speed, it may create problems in other points. So it's not solving the issue. The only way is to reduce the excess of traffic. That's the only way to get out of congestion. You have to reduce the input traffic, full stop. No other way to solve really the problem. There are many approaches that have been adopted and studied. I would say that at least for 30 years, maybe more, maybe 40 years, to deal with congestion, to solve the congestion, to get out of the congestion, to control the congestion, many different things, right? The most trivial solution is to say, I don't care. So I don't care means that I have a given buffer space. As long as I can store packet, I do that. Otherwise, when the buffer is filled up, I drop. And at the end, it is working. I mean, the network is still working. It's not that it's not working, right? And you add on top of that retransmission mechanism end-to-end. So you basically rely on the NG system that when detect congestion, they will retransmit. So it's not really solving the congestion problem. You survive with it. There is a loss, you retransmit, so you avoid losses. That's it. But the congestion is still there. You are not really solving the congestion problem. There are mechanisms which are so-called credit-based, with very different level of sophistication, with many options and tons of papers. Okay, you can go to the literature and read many, many papers on credit-based approach to solve the problem of congestion, from the more sophisticated one, which guarantee absolutely no congestion is possible, etc., etc. What's the basic idea here? The basic idea is that I will control my flow of data in my network in such a way that I will never overflow a buffer. That's the intuition. If you think about that, why you create a problem here in this link, in this buffer? You create, and when? You create a problem here when you receive more packets than the amount of buffer space that you have here, correct? But if you can send from the upstream link a packet only if I give you a grant to do that, I give you credit, and the amount of credit that I give to upstream node is never larger than the amount of buffer that I have, no problem, right? That's the basic idea of credit-based mechanism. So you assign credit to upstream nodes depending on your buffer size. Now, how to distribute the buffer position is a matter of question. How do you do that? How frequently you do? There is a huge spectrum and huge possibility of variation on the basic idea. But the credit-based idea is very simple. I give permission only up to the number of buffer space that I have, position. Not more than that. If you do that, by definition, you will never exceed the buffer size, and you will never have drops, and you will never have congestion. What we are doing here is that one node will give credit, and the node will credit to the node above, and so on, until you reach the user. So basically, we are shaping the user traffic in such a way you will give permission to send only when you have enough buffers to reach the destination. Otherwise, you will not get the credit. That's the idea. Is it clear? It works? Yes. It is simple? No. It's very complex. How do you distribute the credits? How often you do that? How you divide the credit among the users, etc., etc. It's very, very complex, and the scaling, the complexity is scaling linearly with the number of connections you have in your network, because you have to do that connection by connection if you want to do that in a reasonable way. There are more rough way of doing that. It's not connection based. You can do that on a link by link basis, etc., etc. So there are many, many options that can be taken in this idea. One of those options is called back pressure. So back pressure is something slightly different. You don't give credits periodically, so you are free to send unless you get a back pressure signal. It's a stop, for example, signal. There are, again, also many ways of doing back pressure. So you don't transmit only when you have a credit. You are free to send unless the downstream node stops you, unless the other node tells you stop or reduce, or now you can send only 3 packets more or something like that. That's called back pressure. So it's a mechanism similar to the credit one, which is activated only if there are problems. The pure credit base is always active. You keep sending credits, right, to make transmission possible. In this case, you don't send credits, but you send permission to send, or permission, what's the English name of that? You forbid transmission when you have problems, okay? You don't grant transmission. You stop giving grants. And of course, if you do that, after a while, you have to again say, okay, now you can send. It's something similar to what you do in flow control, if you think about that. In flow control, is the receiver which is sending permission to send to the transmitter to avoid receiver overflow, right? Something similar to that, but for congestion based. That's called back pressure. I'm pressing back. Back means on the upstream nodes that are sending data to me. I'll tell them stop or reduce or whatever. And these nodes, of course, may become problematic because now they cannot send anymore, and as a consequence, they will further stop, etc., etc. Okay, until again you will reach the source which are generating the packet. Okay, so that's the credit-based approach. Another approach is signaling-based. So basically, you tell the user that there is congestion, and you hope that user cooperate with you by reducing the rate, or you enforce user behavior in terms of reduction of the rate in the standard. There are, again, all of them are families of approaches. Within each of them, you can find tons of options. Okay? For example, the signaling capability can be very rough, so I can only say I'm congested, I'm not congested, 1 bit, or a little bit more sophisticated, or can reach a point in which you have even an explicit rate assignment. So I will tell you, okay, now send at 10 megabit, now send at 3 megabit, now send at 2 megabits. You see that there is a full set of different options, again, in terms of efficiency, complexity, etc., etc., etc. But the idea is that whenever there is a congestion, you signal. You tell the user what to do. Okay? So these are 3 families of approaches. We will see all of them. All of them rely on a basic concept. We rely on cooperation. Some of them rely on cooperation internal to the network, for example, the credit-based. Some of them rely on the user, on the end system. Some of them may rely on the end system in the sense that you need to put in the access nodes what is the equivalent behavior that you would expect from a user. So you may have a solution which is only internal to the network by, for example, shaping at the user access. Okay, so suppose that you have a control in which the user should obey a given command. You don't want to put this burden on the user directly. So suppose that you tell now the user send at 10 megabits per second. The user doesn't know that. So he keeps sending at 50. You can put in the access node a control which is shaping the traffic at 10. This is a solution which is transparent to the user, right? Is signaling based. So there are many, many options, many different scenarios. We have to define what we want to do. Having a fully network control scenario can have advantages in terms of how much you are secure that things are going to work. But of course, it puts a huge burden on the access node in terms of control. Relying on the user, of course, scales better because it's scaling naturally with the number of users. So if the number of users double, you have also double of the devices which are operating to run the control. So from the network perspective, there is no complexity increase. But at the same time, if the users are not doing what you are expected to, you may have control problem in your network. So there are many, many options, and we're going to discuss some of them. Okay. Some features of these approaches. Dropping is easy, and it can be done without having a concept of a flow or a call or connection. I don't care. I drop in the packet, full stop. I can do that even if I don't have a knowledge about what a flow is. And that's why in the internet with no QoS extension, that was the approach that has been followed. I have no notion about the connection, I drop in the packets, and then I rely on the end system to react. The credit base may be very, very complex. Huge complexity in the credit-based management. You must be flow aware unless you want to block a link. You can have a credit-based mechanism link by link. But if you have a single flow which is congesting a link, you block the full link, which may be shared by many, many other flows that may be passed through this node and go in another direction. Where is it? Here it is. You may have a scenario in which you have a problem here and you want to block the upstream flows, right? But if you block the link, you may block also a traffic which is coming in here and willing to go on another output port because you block the link, not the connection, not the flow. If you want to have it efficient behavior, we will come back to this. If you want to have an efficient behavior, you must run your credit-based mechanism on a connection basis, independently per connection. And this is not scaling well. Okay? So this is an example of what I'm expecting from you during a discussion in an examination. Okay, tell me which are the mechanisms that you can use, which are the advantages and disadvantages, characteristics, okay? So the credit base may be very, very complex. If you want to simplify, you can do that, but the properties that you get are not so nice. And if you want to avoid to block a link, it must be connection aware. Signaling is a hybrid scenario in which you can trade complexity versus efficiency or effectiveness, depending on how complex the signaling scheme is, okay? And it can be used both in a flow aware or in a flow unaware fashion, as we will see. These are the main features of these approaches, okay? I think it's almost time to stop. We are, wow, reached 3 minutes. And why we're talking about that in frame relay? The main reason is that in frame relay, some approaches to deal with congestion have been standardized, and the reason is that a frame relay network properly run should not create congestion, if not of a short period of time. That's the issue. Why? Because if you control that the summation of the CIR over any link over which you route the virtual circuit is not exceeding the link capacity, if you do that, by definition, you will never have excess of traffic in any link, right? Unless for a very short time scale, shorter than the time window over which you measure the CIR, correct? So the only reason why you may have a long-term congestion in frame relay is because you are running the network, tricking the user, cheating the user. You are doing overbooking. You are not allocating what you promised to allocate by the contract. That's the only way, the only possible reason why you may have a significant congestion in your frame relay network. Okay? As such, you cannot say, I don't care. It's not fair. You already are on the wrong side. You should have avoided congestion at all, and you didn't do that because you didn't run in a proper way your network. That's not fair. That's breaking the contract with the user. You have to do something about that. Even if you do something in an optimal way, you get out of congestion by reducing the rate, you are not on the right side because you are not satisfying the user requirement. But at least you avoid this unpleasant phenomena of retransmissions and throughput that potentially can go to a very low level if the network size is significant, okay, due to the phenomena that we have described previously. So in frame relay, you cannot accept saying that I don't care about congestion, the only thing that I do is that I drop packets, and then it's the task of the user to manage that. This is not acceptable, okay, because the network quality of service model was bitrate guaranteed, and if you guarantee the bitrate, congestion should be avoided. If not, it's your problem. That's why this is being run here. So we need to control congestion, and I will tell this, give you this example, which is written here next time, which is going to be Thursday, about why it's also so important, because we don't have in this scenario, remember, in a frame relay network, we have no flow control. Now, flow control and congestion control are completely different things. But if you have a mechanism which is implementing flow control link by link, somehow this mechanism is reacting if there is congestion. It's reacting in a very bad way, but it's still doing something. But in this case, we don't even have that. We don't even have flow control link by link in frame relay. So we absolutely need to do something about congestion. Okay? Any question? Okay. We will meet next Thursday. Maybe, I don't know yet, maybe we will stay here a little bit more than the 3 hours next Thursday. So that can be another recovery class of 1.5 hours. I don't know yet. I will let you know by email. Sorry? Until, yeah, maybe it's not exactly 7, maybe a little bit less than that, but yeah, more or less, yes. Okay? I'm not sure. I'm not sure about the availability of the room yet. Okay, see you Thursday.